Now let's do some questions on Lewis structure and understanding molecular bonds. First one, draw the Lewis structure for CH2O. This one's fairly simple. The first thing we should do is calculate how many valence electrons it will have. And carbon has 4, the hydrogens will have 2, and the oxygens will have 6, making a total of 12. So within the bonds and the lone pairs, we should have 12. Now, carbon is always going to be the central atom, and it's never going to be hydrogen. So we know that hydrogens will be attached to this carbon. And then the oxygen will have the remaining 2 bonds, since oxygen likes to have 2 bonds, and it will have 2 lone pairs of electrons at the end of the day. So that is how you would do it. If you want to do it from scratch, you'd have your 4 dots there, 1 dot on hydrogen, your 6 dots on your oxygen, and the only way for the octet rule to be met with the oxygen and the carbon is for a double bond to form between oxygen and carbon, and a single bond between the hydrogen and the carbon. Okay, so now a little bit more complicated one. Draw the Lewis structure for iodine dioxide difluoride ion, IO2F2 minus. Note all the atoms are bound to iodine in the middle. So iodine has 8 valence electrons, nope, 7, sorry, has 7 valence electrons. That's 6, 7. And then fluorines, you know that fluorines are always going to have 1 bond. That is a definitive rule almost every single time, that if you see fluorine, it is single bound all the time to the central atom. So we can just get that out of the way right now. Then we have O2. So we have our oxygens, we have 2 of them. And we know that there's a minus charge somewhere. Now here's a little tip. Whenever you have charged ions and you're drawing the Lewis structure for them, the best thing, or something that you could assume, is that oxygen has the charge. So if you ever see a single bond to an oxygen like this, this is going to be the charged oxygen every single time. And that's because of its formal charge. So in this case, the formal charge of oxygen would be 6, which is the valence electrons, minus the bonds, which is 1, minus the lone pairs, which is 1, 2, 3, 4, 5, 6, which is 6. Then that equals a total of -1. Therefore, the charge is going to be -1 on this oxygen. This occurs a lot with sulfate, with phosphate, with nitrate, with nitrite, sulfite, carbonate. Most of the different polyatomic ions that have oxygen, the charges are -1 on the oxygen. It's very rare that you'll see a charge on the central atom. So keep that in mind. With knowing that, it makes a lot of our work easier. So we can say that one of these electrons, because the Lewis structure does have a negative charge, will be single bound to the iodine, while the other one, since there's no other charge, will have to be double bound to make our formal charge 0. And this tallies up our iodine. It will definitely exceed the octet rule, and we'll see that it's 2, 4, 6, 8, 10, 12 electrons total, and then nothing else will really exceed the octet rule. It's very important that the very electronegative atoms in a structure don't exceed the octet rule and have the lowest formal charge, if there is a formal charge. So, except for oxygen. Oxygen likes to have, well, not likes, but when you see oxygen charged, it's going to have a formal charge. Or if we see a molecule charged with oxygen, oxygen is most likely to have that formal charge. Okay, so let's draw the structure for SOF4. So sulfur, another strange atom, is underneath oxygen. It has 6 valence electrons, just like oxygen, but it also likes to, I don't know why I drew it like that, but it also likes to partake in not just 2 bonds, but sometimes 4, but a lot of the time 6, like you see in SF6. So knowing this kind of shorthand information can help us a lot. So I'm going to redraw this. Now for fluorine, we know how fluorine works. Fluorine, single bonds all around. So it's going to have 4 single bonds. And what you notice is that, wait, 1, 2, there's another electron. So there's 2 electrons remaining that on the sulfur. And we know that oxygen likes to partake in a double bond, and this molecule is not charged. So nothing should have formal charges. That's another key thing. If there's no ion involved, then there should not be any formal charge, or there should be a net zero formal charge. Let's put it that way. So fluorine, you have a 0 formal charge. Sulfur, it would be 6 minus the atoms or the bonds, which is 6, and then the lone pairs, which is 0, and that's going to be 0. So that makes sense. And then oxygen is going to be 0 as well. Fluorine is also going to be 0. So this is the best Lewis structure. Next one, which of the following ionic compounds has the highest melting point? Now, this corresponds to bond strength. So bond strength has 2 factors. One is the length, meaning the smaller atoms, the ones that are closer together, will produce the largest strength, and the ones that are further apart will not be that strong. And 2, which is the most important, is the charge difference. So if you have +1s and -1s, that will be a lot weaker than +2s and -2s. So for the highest melting point, we need to see which ones are the most strongest ionics. So for that, let's look at the +2s and -2s. Now we have C and D, beryllium oxide and strontium oxide, as the +2 -2s. Now out of those, our next, we already looked at charge, we need to look at the length. So oxygen is the same, it's held constant. Now beryllium is smaller than strontium. So if that's the case, then this must be the strongest ionic bond out of all of these bonds. So it would have the highest melting point. And now which one has the lowest? So we're going to look for the opposite, meaning the +1 -1 that are the furthest away. So out of the +1 -1s, we have E and F, which is lithium fluoride and cesium iodide. Lithium fluoride, lithium is a lot smaller than cesium. Fluorine is a lot smaller than iodine. So cesium iodide is the weakest one, since those atoms are going to be a lot further apart than lithium and fluoride. Meanwhile, you have the other two that we didn't talk about. Cesium's a +1. They're +1 -2s. So they're somewhere in the middle. So cesium iodide is going to have the lowest. Moving on, more formal charges. So based on formal charges, which of these 3 structures contributes most to the resonance hybrid of CNO-? Now in resonance, something that you should know is basically the electrons move around and the bonds flip around. But in some cases, this matters because it changes the formal charge on some atoms. In cases like NO3-, it doesn't really matter, or SO2-, doesn't really matter. Because the double bond on the oxygens, there's 2 double bonds and 1 single bond, they will just keep rotating, and it wouldn't change the formal charge overall of each of the atoms, or overall or on each of the atoms. But in this case, we have different formal charges on each atom in every case. So for carbon, let's just go through it and figure out the formal charges of everything. So carbon here, we have 4 minus the number of bonds, which is 3, minus the electrons, which is 2. That's going to be -1. Nitrogen, the rest we could just do by saying it. Nitrogen, we have 5 minus the number of bonds, which is 4. So it's going to be +1. So we have -1 and +1. This oxygen, we know from experience that a single bond to an oxygen like this is going to automatically have a -1 formal charge. Now let's look at the next one. Carbon, 4 minus 2 minus 4. That's -2. Nitrogen is going to be 5 minus 4, which is +1. Oxygen is going to be, we have 6 minus 6, which is 0. Then this carbon, we have 4 minus 1, 2, 3, 4, 5, 6, 7. So 4 minus 7, that's -3. Nitrogen, you have 5 minus 4, which is +1. Oxygen, you have 6 minus 1, 2, 3, 4, 5, which is +1. So the way I did that so fast is for formal charge, there is a formula, but what I think is I take the number of valence electrons the atom has, such as carbon has 4, and I just subtract the number of individual things attached to carbon. By things, I mean electrons or bonds. That's the easiest way to find the formal charge. So you do 4 minus 1, 2, 3, 4, 5, 6, 7, you get -3. And that works every single time. It's a good shortcut. So now looking at these, something that we should know is that we want to minimize not only the formal charge of the structure, which in this case, they're all the same, but we want to minimize the formal charge on each of the atoms to 0 or +1 or -1, never above 1. If you get above 1, it might be acceptable sometimes, but if there's better options, the resonance structure will take those options. So I basically gave away the answer as being resonance structure 1 because you have +1s and -1s, which are acceptable when compared to a -2 involved or especially a -3. So that's why that is correct. Moving on. So where's the approximate delta H in kilojoules of the following reaction is written? So for this, we are going to do the following idea of the bonds formed, or bonds broken, minus bonds formed. So for this, we need to have an understanding of Lewis structures, and we need to have this chart on hand, the one that's on the right side. And this will be given to you when you need to solve problems involving it. So for the Lewis structures, NH3 looks like this. H2 looks like this. And N2 has a triple bond and looks like this. So the bonds, and we need to keep in mind the coefficients are here as well. So let's add up all the bonds. Each NH3 has 3 NH bonds, all right? So 3 times NH, which is right here, 391. And then we need to multiply that by 2 because we have 2 of those NH3s in the equation. So we can multiply again by 2, or you can change this 3 to a 6 if you want, but it doesn't matter. So those are going to be the bonds broken minus all the bonds formed. So you have HH, which is, according to the chart, where is it? 436. So you have 3 times 436 because you have 3 H2s in the equation, plus just 1 bond of N2. And that's going to be a triple bond, that's to be 941. So that's going to be your answer. And so you're taking in the equation all of the bonds broken minus the bonds formed. And your answer will be 533 kilojoules. All right, next one. This one's a great question. It has everything involved. So calculate the approximate enthalpy or heat of reaction for the combustion of 1 mole of methane. What volume in liters of methane is needed to produce 2,430 kilojoules of heat for methane gas at 38 Celsius and 5.61 ATM? ATM is involved. That means, you know, gas laws are coming back, and that's exactly right. So first, we need to understand the equation, combustion of methane. We can't do anything without an equation or a reaction. So methane, you have CH4 plus O2 yields H2O plus CO2 all the time. That's combustion. That's the definition. Now we got to balance it. Carbons are balanced. Hydrogens are not. So we put a 2 there. So now we have 4 hydrogens. We have 2 oxygens, 2 oxygens. That's 4 oxygens. So we put a 2 right there and we are done. All right. First part finished. Now, calculate the approximate enthalpy or heat of reaction of 1 mole of methane. Okay, so the heat of reaction of this combustion reaction, and we know how to do that based on our table. So we can write the Lewis structures for everything, and we can calculate it. So it would be CH4 plus 2 times O2. So that's an O double bond. So 2 times the O2. This is going to be your bonds broken, minus the bonds formed, which is a water molecule, 2 of them, plus a CO2 molecule, which is C double bond O's. All right, so now we can add up the numbers for the bonds. So we have 4 CH bonds. So we're going to have 4 times the CH bond is 413, plus 2 times the O2 bond. The O2 bond, double bond, is 495. Minus, those are all the bonds broken, minus the bonds formed. The bonds formed are OHs, and there's 2 of them, 463. So, okay, in water you have 2 OH bonds. But in this equation, you have 2 waters. So you need to do 2 times 2, which is 4, of the OHs. So 4 times 463 plus 2 of the CO2 bonds, which is CO double bond, 799. So 2 times 799. Now this heat of reaction will equal negative 808. And that makes sense. This is combustion. Heat is being released. So that makes perfect sense. Energy is being released in a combustion reaction, so it should be negative. All right, so now this is the amount of kilojoules per 1 mole of methane. And the reason why we know it's per 1 mole is because the reaction tells us it's 1 mole because of the coefficient. If this was 2 as the coefficient, we would need to divide this answer by 2 to figure out the kg per mole. kJ per mole. Next part of the question. What volume in liters of methane is needed to produce 2,430 kilojoules of heat for the gas at those temperature and pressure? Now, if you know that 1 mole produces 808, how many moles produces 2,430? All right, so we can divide those into each other. So we can take 2,430 divided by 808, and we get very close to 3. So 2,430 divided by 808 is going to be 3, in essence, 3.007. So we'll just say 3, make it simple. That's going to be 3 moles of methane. That is how much we have in this hypothetical example. So now it's saying what volume of methane is needed to produce that amount with those parameters. We have our moles. We have our temperature. We have our pressure. We're looking for liters. Ideal gas law should be the first thing you think of. And that's exactly right if you were thinking it. So PV-NERT is back. PV equals nRT. Our pressure is 5.61 atm. Our volume is unknown, so write it as V. Our N is exactly 3. An R is 0.08206. And our temperature has to be converted to Kelvin, which is 38 plus 273, which is 311. So it's going to be 311 on the bottom right if you're looking at the screen. And then we can divide the right side by 5.61 to come up with your liters. For volume, you get 13.6 liters. That makes sense. 3 moles of methane. That's a pretty good chunk of methane. And then 13.6 liters. That makes sense. It's not a crazy amount. Okay. This question is a great example. It covers all the bases in this class so far, such as stoichiometry, gases, enthalpy, heat. It really covers everything. I love this question. So if you have any other questions that you have for any of these examples, please write it in the comments and be sure to like the video and subscribe to the channel for more. Thank you.